previous lecture, we looked at supply-side adaptation options, but the soft options. We're going to move on now to look at hard adaptation options on the supply side. This generally involves some kind of infrastructure development. When we're talking about infrastructure, it can take many forms. Some of them are small and quite simple, and some of them are massive and complex. The small and simple ones are often what we would call off-grid, a bit like electricity generation being off-grid if you have a solar panel and on-grid if you're plugged into the power network. Examples of these small and simple off-grid infrastructure solutions include putting in a borehole either for a community or on a farm, building a small dam on a farm to supply your irrigation needs, or perhaps rainwater harvesting where you capture rainwater for domestic or for agricultural use. Over much of rural Africa, small scale is probably often the best solution in terms of infrastructure development. It's locally managed and owned and maintained by the local community, and it's simpler to maintain as well, where you have water resource systems that are not well established or not well supported, that makes the local water supply less dependent on there being expertise and capacity in a bigger water resource system. When looking at hard adaptation, it can either be used to adapt an existing system, a water resource system that might become stressed by climate change, or to ensure that a new water resource system is well adapted. In rare cases, hard adaptation might require a shift to a new system. And a good example of that would be in a groundwater source in the coastal zone, where with sea level rise, the seawater will inundate and push through and replace the fresh groundwater, making it unusable. So you'd have to shift to a completely new source of water and have a new infrastructure development rather than adjusting an existing one. We're going to look at two examples of small-scale infrastructure. The first of those is rainwater harvesting. In fact, rainwater harvesting has been around for thousands of years. It's been used across the world by different societies to capture rain before it leaves the local area and store that rainfall for later use. Traditionally, the capture happens before it enters the rivers, either by capturing water that's flowing over the landscape or from the rooftops of buildings. Some people consider tapping excess river flow in flood periods in rivers to also be rainwater harvesting, but that probably fits better in the river-based water supply system sort of categorization. One of the great things or opportunities with rainwater harvesting is in the modern world, with new materials, the efficiency of rainwater harvesting can be improved. So with plastics and concretes, they generally work much better than some of the older materials that were used in traditional systems. And it makes rainwater harvesting viable in areas where there previously wasn't the natural material available for rainwater harvesting. Now, rainwater harvesting isn't sort of the solution to all our problems. It's small scale, which means that because it's small systems such as these, there's often not enough water available to see through the dry period. So it might be part of the solution rather than the whole solution. Secondly, we can have water quality problems associated with rainwater harvesting. So the systems within which the water is stored are often not that well maintained, and because they're small, they can be subject to pollution problems cropping up much more easily than in a large reservoir where we have, if you like, good dilution properties. Another example of small-scale hard infrastructure development for adaptation is tube wells. Essentially, tube wells tap into shallow groundwater to supply both agricultural and domestic users with water. A tube well is a tube essentially that's drilled into soft sediments, typically in river floodplains. It can go down somewhere between 10 and 100 meters, and it reaches the water table where the groundwater is sitting. The tube is lined with cement or with metal or with some other pipe, and a pump at the bottom running off diesel or electricity pumps water up the well and stores it into a small tank that is then available, that makes the water available for later use whenever people need it. Tube wells have transformed small-scale agricultural farming across a lot of South Asia and also in parts of Africa, particularly in areas where there are these shallow groundwater sources. Millions of farmers have managed to intensify their production and move out of poverty. Essentially, before tube wells were there, they might be lucky to have one season where they could produce one crop. Now, with all year-round water supplied by the groundwater tapped by tube wells, they can produce 3 or 4 cycles of crops, which then moves them from being subsistence farmers into farmers who can sell produce and make money out of their farming activities. But tube wells do have negative issues as well, sustainability issues. In the Ganges, for instance, in the Ganges River Basin, there are hundreds of thousands of tube wells that have tapped into shallow groundwater in the floodplain, but that's led to groundwater depletion through over-abstraction by all these farmers, and the levels of groundwater have dropped sometimes up to 15 meters, which has led to the need for drilling these tube wells deeper, and the costs of pumping have increased as well. Climate change model projections show that suggest that there'll be drying over the Ganges River Basin. The water comes from the Himalayas and there's less rainfall predicted there, which then leads to lower river flows and less recharge of the groundwater system. So what we have here is a case of potential maladaptation, where an immediate solution, tapping groundwater, which leads to depletion, which is then exacerbated by climate change, leads to a long-term problem of farmers running out of water at some stage in the future. Another example of a negative effect of tube wells comes from Bangladesh. Tube wells were implemented across much of rural Bangladesh as an excellent solution to provide good quality and reliable drinking water to rural communities. What wasn't realized at the time was that there were high trace levels of arsenic in the water because the water hadn't been tested for those trace elements. This has led to systemic and widespread poisoning through arsenic of the population, with a whole range of health outcomes that are only now being realized and have had long-term effects on those rural communities.